Welcome back to the next video and to the new chapter, everybody. Today we're going to go into chapter 9 of my notes, covering the construction of the universal deformation ring from chapter 8. So let's get into it. Today will just be a little quick overview of the situation. The setup is that G will be a profinite group and K will be a field. A K representation of G will be a finite dimensional K vector space with discrete topology equipped with a continuous K linear action of G. If V is a K representation of G and A is a complete local ring with residue field K, we'll say a deformation of V to A is an isomorphism class of continuous representations of G to A that reduce to V mod the maximal ideal M sub A of A. And we'll denote by DVA the set of such deformations. So this is all old theory from like chapter 1 and 2 of my notes. We're just kind of reviewing the terminology, the notation, etc. The goal of the chapter will be as follows. We'll let V be an absolutely irreducible K representation of G. As hinted to, in fact, as much more than hinted to in chapter 8, we're going to seek to construct a ring R called the universal deformation ring associated to this setup, representing the functor dv dot. So see the chapter 8 videos for what I'm talking about here if you don't know what a representable functor is. Okay, there's 3 steps to the construction that we're going to follow. First, we're going to let G be a finite group, and we're going to consider a functor that assigns to A a certain class of homomorphisms G to GLN of A. And we'll show that that functor is representable. Then we'll take the projective limit over the situation and obtain a similar result for arbitrary profinite G. And then lastly, we'll pass to the closed subring generated by traces of the elements of G. And the resulting ring will have the desired property. That's going to be our universal deformation ring. Okay, so just a quick remark. In Weyl's proof of Fermat's last theorem, we only actually need the existence of deformation rings for absolutely irreducible representations V, and the fact that these rings are generated by the traces. And so the plan of action that I outlined above is well suited to our goals, but not necessarily as general as it possibly could be. We will explain some more general results at the end of this chapter, though, just for fun. Okay, some more setup. So let O be a Noetherian local ring with residue field K. We'll denote by C the category of local topological O algebras A, satisfying 2 conditions. O to A mod MA is surjective. In particular, K is also the residue field of A, like it is for O. And also, we want the map from A to the projective limit of its discrete Artinian quotients to be a topological isomorphism. Okay, that second condition is actually equivalent to the assertion that A is complete and that its topology can be given by a collection of open ideals A for which A mod kind of frac A is Artinian. Okay, and then morphisms of C will be what they should be, continuous O algebra homomorphisms. Okay, so reviewing a couple definitions here and then some more definitions and then the main theorem of the chapter. We'll let O and K be as above, and we'll let A be in our category C, and we'll let G be a topological group. A representation of G over A, or an A representation of G. So this is essentially the relative theory, whereas we just gave the absolute theory above. This is a finitely generated free A module M with a continuous A linear action, where we give M the product topology via an A module isomorphism from M to A mod N over A. And this topology is independent of the choice of isomorphism. Okay, so we'll say 2 representations over A, M and M prime, are isomorphic if there is an AG module isomorphism. So that's an A module isomorphism with a G linear action over A, M to M prime, and we'll denote this by M is isomorphic to M prime over AG. Okay, so we have a group ring module isomorphism. Okay, so how about relative deformations? Let's let V be a K representation of G. A deformation of V to A is an isomorphism class of A representations W of G, for which W tensored to K over A is isomorphic over K bracket G with V. So that's exactly what you think it's going to be. We'll write DVA for the set of such deformations. A morphism F from A to A prime in C induces a map F lower star from DVA to DVA prime, sending the class of a representation W over A to the class of none other than W tensor A prime over A. So throughout this chapter, V will be a representation of a profinite group G over the residue field K with a discrete topology, like I said above, and we're going to be working over a Noetherian local ring O. Okay, so here's the main theorem of the chapter. Theorem 1, the universal deformation ring. If V is absolutely irreducible, then 4 things are true. There is a ring R and C and a deformation D and DVR, such that for all rings A and C, there's a bijection between C maps from R to A and DVA, and all it is it sends F to F lower star of D. Okay, so this is kind of the main thing that we want to know. This is like the universal deformation ring exists, and here's its universal property. 2, the pair RD is determined up to unique C isomorphism by the first property. That's just basically category theory nonsense. 3, R is not Noetherian if and only if the K dimension of the first cohomology group G and KV is finite. 4, if R is Noetherian, then R is M-adically complete, or M is the maximal ideal of R. And for each A and C, there is a well-defined bijection from O algebra maps from R to A and DVA, and it's the same map as from number 1. It sends F to F lower star of D. Okay, so a couple of closing remarks. Recall that V is said to be absolutely irreducible if V tensor K over little k is a simple uppercase K bracket G module for every extension big K over K. The H1, the cohomology group from above in property 3 of the theorem, denotes the continuous cohomology group of the discrete G module NKV. So not just all cohomology, but continuous cohomology. We do have topology we have to consider here, on which the G action is given by, let me just remind you, it's G phi of V is just G phi of G inverse V for phi in NKV and V and V. This is just the usual adjoint action. We've seen it several times in my list of videos. Also, like I said above, 2, the universal property or the uniqueness stuff from the theorem follows immediately from 1 by usual uniqueness nonsense for universal objects. And then property 4 here. So this situation where R is Noetherian and we conclude that R is M-adically complete, and then we have the same bijection as from number 1. That actually follows from 1. I mean, 4 and 1 are so similar here, right? So why does it follow from 1? All you have to do is prove the following proposition, which we'll do in a later video. But you should think about why 4 follows from 1 given this proposition. Here's the proposition. Proposition 1, let A and C be Noetherian. Then the topology on A equals the M-adic topology, and A is M-adically complete. This is like a standard abstract algebra exercise, I would say. Maybe not exercise, but it's a standard kind of commutative ring theory fact. Furthermore, every O algebra homomorphism A to A prime with A prime and C is continuous. Okay. So we'll start doing all this stuff next video, and I'll see you then. Thanks for watching.